All right, how's it going? So any questions? PA5 or otherwise? I posted a note this morning about SLPs. It's probably too long to read, but for what it's worth, I just want to make sure people understand like the opportunity that SLPs represent. It's probably the most important thing you'll do at Clark, at least as far as your computer science classes go, once you're done with Clark. Your grades obviously matter, all your courses matter, but when you get to a job interview, for example, nobody's going to be terribly impressed that you completed PA3 and you got an A on it, right? I'm impressed, right? I think that's fantastic, and you should feel great about that. But when you're sitting in an interview across from someone, they're like, so why should we hire you? You know, what have you got that these other 50 people waiting to come and talk to me don't have, right? What are you going to tell them? Well, you know, your project that you chose and worked on and researched and managed and, you know, got to a point of completion and presented to the entire school, that can be a fantastic talking point. You know, particularly if it's something that you really kind of throw yourself into and you really stretch yourself, you learn new things, you solve problems that nobody asked you to solve except yourself, right? And that's the kind of stuff that somebody who's looking to hire is going to just totally eat up. It's going to make them very interested in you. And then when they go in and they start looking at your skills, right, it's on top of this person is a real go-getter, this person is a problem solver, this person has initiative, they have drive, they have passion, right? That's the kind of stuff that's going to make the biggest difference. And to have an opportunity to actually do that as part of your coursework, to actually get credit for it, to have a forum where, you know, the dean of STEM or the president of the college might walk through and talk to you for a few minutes about what you're doing, that's just a huge opportunity, right? Those are the little nuggets from which great things come. Those are the 30-second interactions that you look back on 5 years down the road and say, that was where things changed, right? So SLP can be a pain, like I said, you know, something we put on the back burner sometimes, and then, oh, I got to turn in this thing by tomorrow, you know, and you put something together. I understand that. But if you can frame it in your mind as, you know, this is something that I'm interested in, this is something I want to learn about, and sort of take advantage of that as an opportunity, I think it can be really, really beneficial. And, you know, when I was in school, I had all these projects I wanted to work on, and I had to do it despite my classwork and my homework and studying for tests. And in between the hours, you know, where I was doing school, I was working on these projects, and it was the projects that I always felt the best about. So hopefully you can find a way to take advantage of that and get the most out of it. All right, but anyway, we've got to sort numbers. So let's talk about sorts. Oh, the other thing I want to tell you, so Friday I'm going to do is an open lab again. So if you want to work on past programming assignments, or you're trying to figure out PA5, or you just want to go over other stuff, I'm not going to lecture on new material this Friday. Okay, so I'll be in here. You can bring in your laptop and just ask questions or work with groups or whatever, and it's just an open resource for the day. And if you don't need to do that, you don't have to come in. All right, so sorts. So we pretty much know bubble sort, right? Bubble sort works like this. So you have a set of numbers, and let's say we want to sort from smallest to largest. So bubble sort, we make a series of passes. Each pass moves one number into its correct spot. And we do this by comparing each number to the number right after it or right before it, depending on how we start. And so if we run a first pass on this set of data, what we're going to see is the 10 and the 4 are in the wrong location relative to each other. So we'll swap those. We'll put the 10 up here. And now we compare the 10 and the 2, and those are in the wrong order. So the 2 will go up here, and the 10 will come down. And then the 10 and the 3 are in the wrong order, so the 3 will go up here, and the 10 comes down here. And if you think of these things as like stones in water, right, this heavy stone, the 10 is sinking through this set of smaller numbers and working its way towards the bottom. So it's really a falling rock sort as opposed to a bubble sort. But the light numbers, the bubbles are bubbling up to the top, so I think that's why it's called a bubble sort. So after that first pass, we've done a bunch of swaps, right? Since the biggest number happened to be in the beginning, we swapped it with every number along the way, and eventually it worked its way down to this last position, where now that 10 is sitting in its rightful spot in the output array. Okay, well, a totally straightforward bubble sort. We make a second pass. We look at the 4 and the 2, those are in the wrong position, so we swap. 4 and 3 gets swapped. 4 and 6 is fine. 6 and 5 gets swapped. 6 and 8 is fine. 8 and 9 is fine. 9 and 1 gets swapped. The 10 stays where it was. Now we got two things in their right spot. Alright, so if you have n numbers, this takes n passes to guarantee that everything is sorted. It's actually less than or equal to n passes. Each pass is basically n operations, where an operation is compare this number to the number after it, and if they're out of order, then set one to the other, set the other to a temp, set the temp to this, and so on, swap them, right? So the number of steps in this operation can vary, but it's n things we do. And so this is order n squared. It's a pair of nested for I equals 1 to n loops. And we can embellish it a variety of ways. So each pass can be smaller, because our next pass we don't have to look at these last two numbers. We know those are in the correct spot, so we only have to compare n minus 2 numbers, right? And so this is each pass getting shorter. If you add them up, you end up with an n squared over 2 order of complexity, but still n squared. Another thing we can do is we can set a flag every time that we swap a pair of numbers, and at the end of our pass, if that flag was not set, we're done. Because we went through, and if anything was out of order, we would have swapped. And so if our data was in order to start, we would make one pass through. We would never set our flag saying we had to swap anything, and we could say, okay, our data is sorted. So that can reduce your sort time to a best case order n, and worst case n squared, but still average n squared. So there's little embellishments we can make, but often we don't, because if we're doing a bubble sort, we're just being quick and dirty anyway. This can be a little expensive memory-wise. Now, you don't normally think about memory too critically, but if you have gigabytes of data, moving data between very far apart locations in memory can be expensive. If this was a billion pieces of data and our first number happened to be a 10, we're going to move that 10 into every location in our array. Right, we're shifting our whole array basically. That's potentially really expensive. So from a software perspective, an array is just a bunch of numbers. From a hardware perspective, it's a different story. So here's a sidebar are that you might not normally hear about. Here's your memory. Okay, let's say it's 1 gigabyte. If I take a piece of data here and a piece of data here and a piece of data here, that's all pretty efficient. Well, actually, the first piece of data I access is really inefficient, right? Our computers run at 3 or 4 gigahertz, right? So billions of operations per second. If we're doing things like saying, take the contents of this file register and add 1 to it, or take these two numbers and compare them to each other. But if our CPU says, give me the contents of this memory location, and it's not a memory location that we've accessed before, that can take millions of clock cycles. Okay? Your 3 gigahertz processor now goes down to effectively doing, a few thousand things a second. Right? It can take you millions of clock cycles to access 1 byte from memory. Because main memory is really inefficient. Okay, main memory is this DRAM chip, this DRAM card with these chips on it that you plug into your motherboard, right? And if this is your motherboard and this is your CPU and your DRAM is sitting over here, and this is 6 inches away, just to send a signal from the CPU to the RAM, it's going to take you on the order of 6 nanoseconds. And to get a piece of information back from the DRAM is another 6 nanoseconds. So 12 nanoseconds, just to transfer information between the CPU and the memory and back. Well, if it takes 12 nanoseconds to read memory, to request a location and get it back, you can't do that 2 or 3 billion times a second. Right? You're down below 100 megahertz already. Because a nanosecond is a gigahertz. Billion times a second, billionth of a second. So now you're sitting at about 80 megahertz. So what do we do about this? Well, we have inside the CPU a whole bunch of transistors called an L1 cache. It's a local copy of main memory. And the first time you try to access something, it takes a really long time, okay? 12 nanoseconds, that's just the transmission time and reception time, okay? Once you get here, you've got 1 billion pieces of data, or 16 billion pieces of data, and you're asking for 1 byte. Well, you got to find it, right? Go to the library and try to find the 3rd letter in the 5th word on the 7th line on the 819th page of this book. Right? And you got to find the library elevator and you got to know where the book is. You got to take the elevator up, you got to walk over, you got to go down the hall, get the little stool so you can reach up and grab the book, flip to the right page, count down, find that, right? That's all stuff that happens in hardware. And you're trying to decode a single byte out of 16 billion bytes that are stored. That has to be decoded. That takes time. And it's even worse because we have this thing called virtual memory, right? Where chances are that sometimes you access a location in memory, it's not stored in memory, it's stored on your hard drive. Why? Because we might have a few megabytes of a few gigabytes of main memory, but our code might think that our address space is, 50 gigabytes. Well, we can't fit all that into physical memory, so it goes off on disk. And when you want something from this location of memory, the operating system kicks in and takes what's in memory, saves it to disk, goes to your swap file, pulls out the chunk of memory that was stored there, loads it into main memory. That just gets it in here, then you've got to go address and do the transmission time and so on. That all loads it into your cache. Okay, that's where you're talking millions of cycles. So accessing this first location in memory, really expensive. Okay. Next location will be pretty quick. Why? Because when I ask for this location in memory, the computer's smart enough to say, I know your tricks. You're probably going to want the next location too. So it will grab a whole bunch of memory around the location that I just requested. And since it's going over here and going up the library and climbing up the shelf, it's going to grab a whole bunch of information from there. And it's going to send it all to the CPU, and the CPU is going to store it locally. And now I want this next location, and the CPU says, oh, I got that right here, right? And now I'm running at my full 2 or 3 gigahertz clock rate, right? But this is a small amount of memory. And eventually, I'm going to ask for another location, and it's like, oh, that's not in my cache anymore. So it's going to have to go off to the hard drive or the main memory, right? So if I have a billion pieces of data and I'm swapping, I'm accessing every single location in here, each pass through, that's expensive. So a first order analysis of the algorithm, right, may look like it's order n squared, but there's hardware realities in there, just from the reality of accessing so many different locations in memory. So some of these methods that we're going to look at for sorting do a better job with really large sets of data because more of the interaction is local. Some of them are horrible because they just grab data from here and there and there and there and there, and they lose that locality that cache is trying to leverage by saying if you got this location, you probably want a location near it pretty soon. All right, that was a big long sidebar in an area called computer architecture, which you'll probably take whole courses in. But it's a cautionary tale that even if you're strictly a software person, you never want to touch hardware again, you're still dealing with the hardware. And good software design often requires a knowledge of the underlying hardware and what those hardware processes are. All right, so we got bubble sort. 2 other order n squared sorts to talk about. So the first one is called a selection sort. And I'm going to visualize these sorts as basically taking an input list and producing an output list. So there's an incoming list of numbers. We want to sort it. I'm just going to stick to smallest to largest. Okay, so selection sort, there's a selection sort and insertion sort. They can be tricky to keep track of which is which. Here's how I think of it. Selection sort, the way we do the sort is by selecting carefully from the input list. Okay, all our work is in how we select from the input. Putting them into the output is painless. Okay, we're just going to put them in the next location one after another. But we very carefully select each element from the input. How do we select? We select the smallest element. So what's the smallest element in the input list? Looks like it's a 1. So I'm going to take that, put it to the output. Now I'm going to go through, I've got to somehow mark this 1 as having been removed. So I'll just put a line through it. Okay. Now find the smallest number in the input list. Looks like it's a 2. Let's put that into our output in the next location and remove it from the input. Okay, what's the smallest number here? Looks like a 4, 4, 4, 4, 4. 4 is all the way. That's the smallest number. Remove it from the input. Okay, how do we find the smallest number in code? Well, this is like you're running minimum for the egg function, right? Start off, let's say 10 is our smallest. 12 is bigger, so 10 is still our smallest. Oh, 6 is smaller, that's our smallest. 8's bigger, 9's bigger, 7 bigger, I guess 6 was our smallest. Okay, so add 6 to your output. Remove it from the list. So mark your smallest as whatever the first entry is, and then as you go through, if you find a number even smaller, just remember that that's your smallest. And when you get to the end, whatever you've noted as your smallest, that is the smallest of the list. How do we add to the output? Just add it to the end of the array. Keep a pointer saying how many things are in here, store it in that location. This will put a 7, 8, 9, 10, 12. So this looks like n squared. Sorry, my throat's like super dry. It is, well, I picked up something on Friday and I'm past the worst of it, but talking makes my throat dry. I could do a puppet show. So this is order n squared, right? We have to process n pieces of data, so it's n passes. And finding the smallest number, that's an order n operation. Okay, how do we remove something from this list? Once we found the one, we put it in our output. How do we avoid picking that on the next pass?
You would mark the number you're choosing to delete by marking it as skip.
So we could have a skip field initialized to 0. And once we find a number, set that flag. So that works. Any other ideas? Yeah. It's just an array, so. But if we had a list, we could delete it and then free it. So that would be another approach. Any other options? Yeah.
Well, if you knew what kind of data you were having, you could pick an arbitrary value that you know you're never going to have. Like if you're looking at numbers of items, you're never going to have a negative number. You just set it equal to negative.
So we could change it to infinity if we're looking for smallest to largest. And then we'll never end up picking that as the smallest. Or give it a value that we're going to exclude, like negatives.
You can also just check if it's already in the output.
You could check to see if it's in the output. That's going to get expensive, though. And that's going to be an order n for each number that we consider. But there might be some way to mark that. So that could be an option. Any others?
Well, to bounce off that idea, maybe for every time you put a number into the out array, you save it to another array, kind of like a full array type thing. Kind of harken back to what we're doing for PA as well as
That could be another way. And those are versions of basically setting a flag somehow to mark this as even though it's in the array, let's not use it. Is there a way to actually remove it from the array that's efficient? We could shift everything, but that's another order n operation.
You just set it to like 0 or something.
You can set it to a special value, like infinity is good if we're looking for a min. Let me show you a trick. Okay, so here's our data. Here's the number of things in our data. We go through, we decide one's our biggest number. Copy the last element of the array to that location. And now just change your number of data items to 8. Since there's only 8 things in our array, this is what our array looks like. We'll never be bothered by the extra 7 down there. Now go through, and our 2 is the smallest thing. Replace it with the last thing in our array, which is a 9. And now that's our array. Okay, fixed amount of time. Basically just one copy operation, just the length of your array. But it effectively deletes a number from the array by moving some other number we care about into that spot. So that can be a useful trick to keep the order efficiency high. All right, so that's selection sort. It's sorting based on which pieces of data we select from the input. The dual to that is the insertion sort. Insertion sort, we don't do any work in selecting from the input, we do our work in inserting to the output. So we just select the first element in the array, and we insert it into the correct spot in the output. Well, our output's empty, so the 10 is just going to go in the beginning. Move to the second number in the input, that's a 4. Insert that into the output array in the correct place. So it should go before the 10. So this will be a 4 and a 10. Find a 2, that should go in the beginning, so this will become a 2, a 4, and a 10. Find a 3, it comes after a 2, it goes before a 4, so this becomes a 3, a 4, and a 10. 1 goes in the very beginning, so this becomes 1, 2, 3, 4, 10. Sys goes after 1, 2, 3, 4, but before 10, so that goes in the 6, and the 10 moves down, and so on. So insertion sort, all the work is in placing things into the output. Input, we just grab the next thing from the array. And we can start from here, we can start from here, it doesn't change the algorithm. So we have to do n passes, because each pass is taking one number from our input and adding it to the output. And how much work does it take to insert into the output array? Best case, you're just adding it to the end. But you don't know that until you've compared everything in here. N operations. Worst case, it's got to go in the beginning, everything gets shifted down. But you only had to do one comparison. But in the end, each pass is basically order n. So this whole thing is order n squared. Is there a way to speed up the performance of the insertion part? Besides having fewer data? I like that thinking though, change the problem. It's always a good trick.
You could make it so you're comparing less things by doing like kind of a high-low.
So you could do kind of a high-low, right? Since our output list is sorted, we could play high-low and it'd take log n to find where to insert our number. But then we still have to shift everything down, which is somewhere between one operation and n operations. So that will be quicker, but order of complexity is still going to be basically n. Say again? Right, if you know how many data points you have, that might help you place them. If you make a linked list and you want to insert a 3, remember the whole idea of a linked list is we don't have to move things down. We can just make a 3 and point to it. So we can eliminate the cost of moving things, but we still have to figure out where does that 3 get inserted, which for a linked list means start at the beginning, follow the links from one node to the next until you get to a node that's bigger, and that might be potentially n operations. And we can't play high-low on a linked list because we don't have pointers to the middle of the list, so that's where a binary tree comes in. So if we were inserting into a binary tree, that's going to give us better performance. Okay, but that's no longer really an insertion sort. It's really just sorting with a binary tree. But that would get us to n log n. All right, so selection, we choose the input element in order. Insertion, we insert into the output in order. Okay, that's the difference between the two. And those are n squared like bubble sort. All right, so let's do better. Let's do a merge sort. So when I get papers to grade, when people turn in homework, I mostly do an insertion sort. I have a stack of papers, they're not ordered. I take the first paper, I put that in my hand. I take the second paper, I put it before or after the first. And I take the third paper, I put it before the first, after the third, or in between the two. And I keep taking papers off the top and putting them in the right spots so that the thing in my right hand is always sorted, right? And then I get a name with a Z in it, and it goes right in the back of the pile. And I get something with an A in it, and it goes probably right on top. And the other ones go in the middle. And when I'm done, when I've taken all the papers from the input, I have a sorted list in my output. Okay, that's an insertion sort. I don't know why I do that, but that seems to be what I do. But I have a different problem when I give exams, because I sit here and I give the first exam and get that stack of papers, and I usually start grading those during the second one, but I have that stack and it's sorted. And in the second exam, as people are turning them in, I'm inserting them into my output stack. So at the end of the second exam, I have a second stack of papers that are sorted. And now I have two stacks, but I want one stack, right? Because when I put in grades, it's all combined into one big multi-section entry in Canvas. So I want my papers all combined together. So I have two stacks of data. One of them looks like this, and the other one looks like this. And this is sorted and that's sorted, but I want to combine them into a single stack. Well, it's pretty easy to do. I put the two stacks down on the desk, right? So here's the top of the stacks, and I just see which one comes first, one or two. Well, one comes first, so I take that off and I put that in my output pile. And now stack 1 has a 4, stack 2 has a 2. 2 is the one that comes first, so I take that off there, add it to my output. Now I'm looking at a 4 and a 3. 3 comes first, that goes on my output. Now I'm looking at a 4 and a 6, so I take the 4. Now I'm looking at a 7 and a 6, so I take the 6. Now I'm looking at a 7 and an 11, so I take the 7. Now there's a 10 and an 11, I take the 10. There's a 12 and an 11, I take the 11. There's a 12 and a 15. And now this stack's empty, this one has a 15, so I take that. So I do this interleaving operation, this merging of these two sorted stacks. And it's a really easy operation to do once you kind of get your mind in the right groove.
But they have to be sorted.
But they have to be sorted, right? So once those are sorted, you just pull off the smallest one from each stack and just keep adding it to your output. And you've got to be careful if this pile is empty, I don't want to compare 15 to the top of the desk and get a seg fault in my brain. I have to know there's nothing in this other stack. And at that point, it's easy. I just take this whole stack and I add it to the output. It just goes right after the last entry. Well, we can turn this into an algorithm. And it's a really fun algorithm. It's called a merge sort. So let's write pseudocode for a merge sort of a set of data with size elements in it. So this is heavy pseudocode. But the spirit of this is I want to make an array containing the first half of the things in my data array. So I'm just saying data bracket 1 comma size over 2. It's a fictitious language construct. Make me an array containing the first half of the elements in this array. And let's sort that somehow. Contains size over 2 elements. And I'm completely ignoring questions like, what if you have an odd number of things in your array, and these aren't going to be the same size, and so on. But I'm writing pseudocode so I can do things like that. So I'm going to sort the first half of the data. I'm going to store that in an array called A. I'm going to sort the second half of the data, store that in an array called B. And I'm going to merge those. And just return the result of merging. So merging is that interleaving. Just take the top element from each array and put it in the output. And that's a merge sort. So split your data in half, sort those. I use an insertion sort when I'm doing papers, right? But sort them somehow. Merge the two sorted pieces together and return that. We don't like insertion sort though, because it's order n squared. So how should we sort these two subarrays? What's a good algorithm to use? Well, merge sort. We got this fancy merge sort that I've said is order n log n. That's pretty good. So let's use merge sort to split those subarrays, to sort them, and then let's just merge them together. So this is very recursive, and it has that classic recursive feel of using itself to solve the problem. And we need a base case. So maybe if size equals 1, we'll just return the data array that we came in with, because it's already sorted, it only has one thing in it. So that ends the recursion, stops us from going endlessly down the rabbit hole. Split your data in half, merge sort each half, and then interleave them together. Alright, so this is order n. Well, it can be tricky to try to figure out the performance of this since it involves calls to itself. But you can do it, you'll do it in an algorithms course. The only time we actually do any real work, other than merging, is right here. Right, if the size is 1, we just return. Otherwise, we're just making recursive calls, right? So we're doing order n. So really the question is, how many times do we end up calling merge sort? Right, and it'll be that many times n. That's probably our order of complexity. Well, if you start with 1,000 pieces of data, you're going to split your data in half, and you're going to do this merge once on a pair of 500 length lists. But you're going to call sort on each of those, which is going to get split in half. And so each time you call merge sort, you're going to end up doing twice as many merges, but you're going to be merging things that are half as long. And you'll keep calling merge sort recursively until your size comes down to 1, at which point you no longer recurse, you just return the original array. Well, if you start off with n pieces of data, it takes you log n divisions in half before you get down to a size of 1. So this turns out to be order n log n. And it takes a lot more work to show that without hand waving, without hand waving. So it's fundamentally faster than a bubble sort, insertion sort, merge sort. Okay, particularly for really big n. If you increase n by 1,000,000, you go up by 1,000,000 times 20. So 20 million as opposed to 1,000,000 squared, which is nice.
But can we do better?
But can we do better?
Has it been proven that there's a point that we can't do better with sorts?
Well, if we lived in sorted world, everything would be order 0, because everything would always be sorted. And I believe there's a way to have a sorted world universe, but things are really strange in that world. I don't know if there's a reasonable upper bound. So here's my standard example. All right, where's the tallest line on that page? Yeah, it's this one right here, right? Was that order n? Was it n squared? If I had drawn more lines on here, would it have taken you longer to find that? Maybe, probably not, right? This is kind of order 1. We could look at this and we could go, oh yeah, right there. Right, how is that happening? I mean, our brains are computers. We've got optical inputs.
You can see everything.
You can what?
You can see everything.
We can see everything, right? But we didn't, you know, go from here to here to here to here to here to here. Somehow we took the whole thing in, right, and processed it. The other example is you know, take a vat, fill it with oil, and get a series of rocks of different diameters. So you have some really big rocks and some really small rocks and some middle-sized rocks. And let them all go at the same time. And the smallest rock is going to hit the bottom first, because it's got the least surface area. And the biggest rock is going to hit the bottom last, because it's got the biggest surface area. Right? And so we can do physical sorts that are sort of independent of the number of things that we're sorting. Right? So there's systems out there that can do better than any of these things that we're learning. Hooking them up is a trick. Taking your data and synthesizing a bunch of rocks, or getting somebody to stare at a picture and tell you.
This picture could be basically a tree, but with a branch for every node of data.
You could probably view it like that, no pun intended. But it still seems somehow better than a tree, right? It feels like you just look and it's like, bam, there it is, right? Or what's the brightest point, or what's the largest object?
I mean, it might take a small processing time.
Yeah, I mean, we have parallel processing going on in our brains.
I feel like the way we're looking at it is you kind of look, okay, which one? Like you just keep going up until you see the top one. So you could decrement every piece of data until only one of them is above 0.
Yeah, so I mean, we're kind of like, you know, going up until there's only one thing, or maybe coming down until we hit one thing. But with our optical processing, we're still not scanning, right? I mean, we look at that and it's, you know, there's one thing there that jumps out. So yeah, there's limits on scalar processing. Parallel processing, it changes things a little. So merge sort is an example of a type of algorithm we'll call divide and conquer. Okay, Okay, we talked about greedy algorithms. Greedy algorithms try to solve as much of the problem at each point as possible. So fractional knapsack problem you can solve with a greedy algorithm. Divide and conquer is another type of algorithm. It's a problem that is solved by basically cutting it into smaller subproblems, solving those, and then putting those subproblem solutions together. Okay, and merge sort is classic divide and conquer. Split your list in half, sort each of those, and then put them together. And divide and conquer is a really powerful technique. It's often recursive. It's often something involving log n in its efficiency. All right, so I want to talk about quicksort next. I won't start it today. I'll start it tomorrow. Quicksort's another n log n algorithm that is basically divide and conquer, but a different feel from merge sort. So we'll talk about quicksort tomorrow. We'll spend some time having you work out some quicksorts on the board to make sure you understand the algorithm. And then we'll talk about heap sort, and heaps are their own data structure, so we'll spend a while talking about that. And then we'll go on to a few other sorts like radix sort and maybe topological. All right, I will see you next time.
Yep.